Thank you very much to Tom and Thierry in particular for inviting me to be involved in this. It's been a very, very interesting day so far. And thank you also for giving me carte blanche to give a talk, a non-standard academic talk. We were asked to talk about the societal implications. And really, this was a real opportunity for me to stop and think about the fact that I've been really obsessed with this problem for now over 30 years, since Paul Linden put into my pigeonhole a conference paper of Greg Lawrence's from the Stratified Flow Symposium in 1987 in Pasadena to say, you might like to think about these sort of problems. And I've continued to think about them, and I haven't really got very far. But I'll try in the next 50 minutes or so to do a whistle-stop tour through the various things that some of the things that I've been involved in, particularly in this project, the mathematical underpinning of stratified turbulence that sadly has finished, which funded 5 years of fun for us in Cambridge, thinking about these sort of stratified problems. But I also am very obsessed with another thing at the moment, and so I thought that there would be an alternative title for this talk that would be appropriate, was that there are at least 5 ways in which stratified mixing is like Brexit. And in the next 50 minutes, I'll try and show you what these 5 points of connection are. The first one, obviously, the societal implications. A lot of people are in real trouble. Unfortunately, I've been meeting many people who are not facing being a citizen of the European Union in the UK after March the 29th, but there we are. There are a lot of us in that circumstance. Secondly, however, there's the issue that Theresa May insisted that Brexit means Brexit without defining what Brexit meant. And there's a similar statement could be made about mixing. There's a real issue. We talk about mixing all the time, but we don't necessarily define what we mean carefully, and that turns out to be extremely important in my opinion. And also, with my Irish passport, the key idea is that what's happening near the boundaries is most important. And we really, I've spent much of my career thinking about free shear flows and so on and instabilities, and I'm becoming more and more aware that it's actually the boundaries that matter. It's not just the boundary conditions that matter, but what's going on near boundaries is really a key part of the activity. But there's another part that's very important too, which also resonates, which is that being free is very different from being forced. If you force the flow to do something, you get a dynamical response which is different from what if it was freely evolving and doing what it wanted to do, and that also resonates with the Conservative Party. And and then finally, and this also resonates with the Conservative Party, and also very much with Matthew's talk earlier, because I think his idea of phases is really got a very, very important concept that we're not really appreciating about how significant it is, which is that history really matters. And this is a real challenge we have with respect to parameterizing flows. Because if we think we have our parameters, our length scales, our non-dimensional parameters, those are an instantaneous statement of the condition of the flow at that instant. And yet I'm coming to the conclusion that the time evolution of the flow is a key aspect, and where it has been before is affecting what the dynamics of the flow is now, even if in this snapshot the parameters appear to be the same at that particular instance. And I'll try and give you some examples of that particular situation. Okay, so why are we interested in stratified mixing? We already heard this morning, it probably is in one of the top 3 of the most uncertain parameterizations in climate science. Clouds are a real problem. The dynamics of ice, while we still have some, is a real problem. But understanding how the ocean currents, like we see here, are reflecting how the heat is being moved around in the interior, this petawatts of heat being transported polewards is really a key challenge for the parameterization of the global climate system. And it's really, really weird what's going on. We've already heard Matthew mention this beautiful paper collecting all the data, this Waterhouse et al. And those different lines illustrates the it's epsilon, the dissipation rate estimated by best guesses. And those are heights above the bottom characterized by different properties of the bottom, whether it is smooth, whether it's rough, or whether it has a ridge. And it really leaps out to me, it's quite amazing that fully a kilometer above the bottom, the properties still know what the bottom was like. From this, that's what this data says to me, and that's really suggests that it's an extremely challenging problem, because of course the mixing processes, these Osmodov length scales are centimeter order in the flow, and yet information is being carried kilometers about structures that are hundreds of meters, kilometers on the bottom. It's a very challenging problem, and so that is what we're concerned about. But it was really, as I was thinking about this talk, it really came home to me just how important this problem is, because in the last 2 weeks there have been 2 articles in The Guardian about it, actually about this specific problem. This is an article on the 7th of January, global warming of oceans equivalent to an atomic bomb per second, which is just a statement of how much energy has been going into the ocean. And then there was this other one from last Wednesday about the evolution of the temperature, the average temperature in the ocean compared to the mean value over the last 50 years. And you'll see that it is effectively a monotonic increase and is proving to get much, much hotter. Now, these are honest, published in proper journals. This was published in PNAS. This was published in some other journal that I can't remember the acronym of. But they're peer-reviewed papers, and these are very good, excellent papers. I looked at them. But they are using relatively simple parameterizations about, as you heat the top, how you transport the heat downwards. And in this room, we understand that those are highly simplified models, and that high simplification then leads to a real challenge about whether we know we're getting the right responses. And these responses are critical, because as you heat up the ocean, it expands, of course. As you heat up the ocean, you run the risk of melting. Heat up the atmosphere, you land-borne ice, and so you increase the likelihood of extreme events. You terribly affect the ecosystems, and literally billions of people rely for their primary protein source from fishing, as well as billions of people live close to the coast. You know, there's the hint is in the name of the Netherlands, right? That this could be a problem if we have sea level rise. And so it's a fundamental question that we need to address. Now, we've heard many today, and indeed I agree a lot with, I agree with virtually, fortunately, with a lot of what Greg says, since we're supposed to be writing some of this review article together. But because the fundamental question that to understand how you're transporting the heat vertically is to do with understanding this kappa, this vertical or diapycnal eddy diffusivity. Because of course, you know, I like to say for the oceanographers that it's perhaps easier for them to measure a mean gradient in the density field, but it's extremely difficult, as Matthew said, to measure correlations between velocity perturbations and density fluctuations. And so then you just do the analysis, you get this quantity gamma, which I like to describe really as, if you think about the energetics of how the turbulent kinetic energy would evolve, you can have a production, which could be due to wall forcing or to a background shear or whatever, and that's injecting energy into the system. And then you have 2 costs. You have the buoyancy flux and the dissipation rate. And really this gamma is measuring the tax rate on this energy dissipation. It's seeing how much of the energy that's being put in has to go in increasing the potential energy of the system, if we average for sufficiently long periods, rather than goes into viscous dissipation. And as you write this expression down and you get this very elegant expression, it then seems to be, okay, if we can say this gamma is constant, as Osborne did in a paper that's got, as of this morning, 1,192 citations, you have, if gamma, you presume that gamma is constant, then you have a relatively simple way of understanding how this kappa goes. But really, there are open questions of order 1 that are not agreed, as Greg demonstrated earlier, and as Matthew said also, about how this gamma behaves. Does it depend on a Richardson number? Does it depend on the buoyancy Reynolds number? Does it depend non-monotonically on either of those parameters? This is a wonderful idea that Hessam Saliapour came up with. You know, is the curve, does gamma depend on Richardson number and buoyancy Reynolds number like the MATLAB logo? But it could. We don't really know. I would argue strongly we don't really know, because there's a fundamental question about whether a flow manages to have actually these two parameters independently. Is it actually possible to have a high buoyancy Reynolds number flow that has a high value of Richardson number? What do you mean by a unique value of Richardson number? Can you end up with a layered situation? And so really, trying to understand this is critical to understanding this, which is critical to having any chance of improving the parameterization beyond saying it's roughly a constant. And so really that's what, you know, the applied mathematician, the fluid dynamicist, the guy who doesn't go out on the boats and measures things with things made out of mobile phones. You know, how can we advise the actual oceanographers, the actual climate modelers, about how to improve those models? And that, once again, very nicely set up. As Greg said, it really can be thought of, you know, you might have some idea of length scales. But really, even if you say, okay, I want to describe it in terms of length scales, there are fundamentally at that two levels of challenge. There is the spherical cow level of challenge, which is if I have a perfect world, if I have a numerical simulation that's properly resolved, or if I work, if my next door neighbor is Stuart DL, so we can measure God knows what in the lab, what would be needed to describe the mixing, which I might describe as perhaps my problem. But then there is this other challenge, which both Matthew and Greg alluded to, which is in the real world, there are certain things you can measure and certain things you can't. And so we really need to understand as a community that these two groups have to communicate. It's all very well developing a super sophisticated model, but if it isn't useful to the operational and cannot be constrained by real data, it's not really particularly useful. So I have some central concerns, and as I say, this resonates with this sort of Brexit means Brexit comment, which is we really need to carefully define what we mean by mixing. And there was that very nice paper by Karen where he said, well, one person calls mixing efficiency this, and another person calls mixing efficiency that, and another person calls mixing efficiency this. And we've really got to be careful about what we mean by mixing, and we've got to be careful to understand that whatever measures we have to be appropriately averaged. And if we have averaging, do we mean ensembles? Do we mean time? Do we mean space? And do we have resolution issues like Greg was talking about? And also then the measures they use to parameterize mixing needs to be defined very carefully. So, you know, a Richardson number is a ratio between a buoyancy frequency and a shear squared. But are these vertically averaged? Are they homogeneously averaged? Do we allow them to evolve in space and time? Are we in a situation where we're able to uniquely identify these quantities or not? Very important to worry about that, because some of the truths that are considered to be self-evident, as I'll come on to mention, could really be associated with people are defining things differently and meaning and seeing things differently, and so therefore drawing conclusions from assumptions which are not necessarily right. Having said all that, we want to know whether we can define things in terms of length and timescales. But there are critical issues about how we define them, and there's also, you may hope that they're not correlated, but they may be. And so Greg was saying, you have this density length, and then you have which is distinct from the shear length or whatever, but maybe they are and maybe they're not. In some situations they're going to be, they may not be correlated. In other situations they may, which as I'll say is kind of related to some of the concepts I'll be trying to talk about later. So, what do we mean by the properties? Well, I think there's at least 4 classes of properties of a fluid, the fluid that we're interested in. There's the inherent properties of the fluid. the viscosity, the diffusivity of whatever you're using to change your density. Of course, you could have multiple such diffusivities. You could have nonlinear equations of state, and they could be causing dynamically significant effects that you're not necessarily modeling. There's the properties of the background. You are often in an environment where you think you have some larger scale shear, where you think you have some larger scale stratification. But even when you are making those statements, you're making some statements about averaging, and so what does that mean? And in particular, how would you understand a situation if these varied spatially? I've been obsessed with saying, for example, that layered situations are very common, and we kind of ignore them, and so that you have a natural variability in the buoyancy frequency. So what buoyancy frequency do you use when you define your buoyancy Reynolds number or whatever is a moot point. There's also, of course, the properties of the turbulence, its intensity, its dissipation rate, and you could interpret that, of course, as its properties of the fluctuation field of the velocity. And I'd like to say, resonating with what Greg was saying, it's just as important to worry about the properties of the density fluctuation field. Not necessarily, though in many situations it's closely related, it is the potential energy, but effectively, if we're interested in mixing, what we're interested in is how those fluctuations in density are smoothed out. That's really what homogeneity is a mixed fluid. If there's variability in it, it's not fully mixed. And so understanding the dynamics of this quantity, you know, like the variance in the density and its destruction rate chi, are also really important things. And I mean, that's what Greg was saying. That length scale his density length scale is effectively constructed from considering these quantities. But then those quantities can be formed into length scales or time scales or non-dimensional parameters. And just like the famous story of the blind men and the elephant, I think we need to be really careful about what we mean when we're talking about mixing and what aspect of the mixing we're talking about, because it really depends on the way you frame your question, the sort of concept you end up identifying. And so, really, can unique values be, even if you say, okay, I want to parameterize something in terms of non-dimensional parameters, can unique values be assigned? If I do assign them, are they correlated? And does the mechanism matter, or does history matter, which is what I'm saying. So then, in the next 30 minutes, what I want to try and talk about is these 7 ideas. So that's, 4 minutes each. So this gamma, this rate, this taxation rate of the buoyancy flux to the dissipation rate of kinetic energy, does that vary with parameters or mechanism or time? If it does vary with parameters, is it possible to access the right flank? And that's like the Greg's idea with talking about knights. I feel that that's my windmill or my unicorn is trying to identify the right flank. And what I mean by that is that it comes from this, obviously very big influence on me, this paper of Paul's from a few years ago. And this is the flux-Richardson number, which of course is related to gamma, with stratification. And this sees that it goes up and then it comes down on the right flank. So there's a dynamical situation where the flow is strongly stratified, and it seems reasonable if the flow is strongly stratified, you'll suppress vertical motions, so you might suppress the flux, the mixing, but you wouldn't necessarily suppress the dissipation so much, and so you'd have this right flank. And similarly, you might imagine that if this wasn't Richardson number, this Reynolds number, you might also have that right flank. You might have, if the flow is very, 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 very turbulent, you'd expect that most of the energy loss is going to go into viscous dissipation and not so much into mixing, and so you'd have a drop-off on the right flank. And we saw this sort of right flank in Greg's data, and the question is, when does that occur, and what is the dynamical behavior that you have in those sorts of right flanks? We've already had mentioned this layered anisotropic, I'm missing a stratified turbulence here, this scaling argument that was originally put forward by Jean-Marc Chamaz and Paul Bion. If you look at the equations, you can imagine a situation where you have very turbulent flows that are still very strongly stratified. And what is the dynamics that you can have in that situation? And the question is, can that actually exist with any conceivable set of forcing? Then that, of course, is a layered sort of dynamic. Is layering ever possible? Is it generic? Does it happen? We always think of sort of a characteristic n squared, but in turbulent flow, if you mix it up, maybe you end up with a layered sort of structure. Does that actually happen regularly? Is stratified turbulence ever generic in any sense? Or is it all very, very specific about its own situation? And then this is the one certainly that cuts to my history. Is linear stability theory relevant to the turbulent dynamics? It seems reasonable that high Richardson numbers are going to suppress flows, but if you have a turbulent flow, you can't really appeal to Miles Howard to make that happen. Though, the pictures do seem to do that, but the mathematician in me says this shouldn't, the argument I'm presenting is not an adequate, it's not a rigorous argument, it works, but that's not the right argument. So there's an open question, fascinating question, about whether mean flows that come from a turbulent simulation, the stability of those turbulent mean flows, are they relevant to the dynamics? And then this observational piece, which is Matthew's problem. Okay, so what have we got? This variation of gamma issue, and there's this very, very influential simulations of Xi et al. And been supported, I call it the Stanford School, which shows this picture. This is the scaled eddy diffusivity effectively against this epsilon over nu n squared, this buoyancy Reynolds number. And they find some regime where it's close to gamma equals 0.2, and then it rolls off at high values, which scales quite close to buoyancy Reynolds number to the minus a half. That still means that the eddy diffusivity increases with buoyancy Reynolds number, but it is increasing more slowly. And there's been a recent paper in GRL by Stephen Monosmith and with other people as well, showing that if you plot the curves appropriately, it does kind of look like you might have this buoyancy Reynolds number to the minus a half kind of scaling. Remembering the issues with averaging and reversibility, if we suppose we have a steady state, we then would be saying that the production, wherever it's coming from, is going to match precisely the buoyancy flux and the dissipation when appropriately averaged. And the flux Richardson number, of course, is just the buoyancy flux divided by this production. And so, in such a steady state, this can be related both to the gamma quantity and also to this chi, this destruction rate of density variance. But this is the Rorschach test of stratified turbulence coming up, because if you remember your definitions of a turbulent Prandtl number, so if you remember that the eddy diffusivity for the heats goes like this, and the eddy diffusivity for momentum goes like that, then the turbulent Prandtl number is just the ratio of the Richardson number to this flux Richardson number. And why I say it's the Rorschach test is because what does that equation mean to you? Very influential paper, the Osborne paper, cites Ellison 57. Ellison 57 cites a conversation with G.I. Taylor. The conversation with G.I. Taylor, I paraphrase, was that since turbulent continues to exist at high Richardson number, that's big, this is a clear efficiency, so it's definitely less than 1. So if turbulence exists at high Richardson number, that means the turbulent Prandtl number must get large. But let's do a Rorschach, it just does, right? Because this is just maths. I'm not making any assumption. So if you say that your turbulent Prandtl number is equal to the Richardson number divided by the flux Richardson number. So the flux Richardson number is definitely less than 1. So if you have turbulence at high Richardson number and it is well defined by this unique value, then that means that the turbulent Prandtl number must be very large. But you could say, you would always expect, if you actually have turbulence, that the turbulent Prandtl number will always be order 1. And that then tells you, you can't have turbulence at high Richardson number. So, what is it? Or which is it? And anyway, even if you just see this expression, since the Richardson number divided by the flux Richardson number is equal to this Prandtl number, it suggests that since gamma is related to the flux Richardson number, gamma might depend not only on the buoyancy Reynolds number, but the Richardson number. So the question is, does that actually happen? Do we know? And I would argue that it is still order 1 undetermined what this is. People publish papers, including me, with strong arguments about how this goes or not, but we don't really understand it. Now, there's this very influential sequence of ideas from, as I mentioned, this last regime, from this sort of scaling argument, because the buoyancy Reynolds number is an appealing choice to say that you might have a regime when you have a large value of the buoyancy Reynolds number. Because as already mentioned, we can express the buoyancy Reynolds number as the ratio of the Osmodov scale to the Kolmogorov scale. And now let's think about what that actually means. The Osmodov scale, as was beautifully described this morning, can be thought of as the biggest eddy that doesn't really feel stratification. It has an order 1 Richardson number itself, if you think about the eddy. So that's really it's eddies smaller than that have enough kinetic energy to overcome the potential energy to spin round, but eddies that big or bigger are going to be starting to be squeezed. So your only chance to get isotropic turbulence is if your scale's smaller than the Osmodov scale. Okay, but if you want inertial range isotropic Kolmogorov religion that you're taught in grad school, you certainly need to have a wide separation between that Osmodov scale and the Kolmogorov scale to have any chance of an inertial range. Therefore, your buoyancy Reynolds number has to be huge. And if you go through the math, you then face this challenge that how am I going to get regions where there is a low value of the Richardson number to then still trigger turbulence? And that implies that you have this hierarchy of scales. You have to have an enormous horizontal scale that is much, much bigger than a vertical scale, that itself is much, much bigger than the Osmodov scale, that itself is much, much bigger than the Kolmogorov scale, so that you have these big old patches that are like spaceships going past each other, and they fight when they come by, because this one is going slowly that way, going slowly that way. So there is enormous vertical shear here, sufficiently large so that your local Richardson number is small, and yet that scale is sufficiently big such that your local Reynolds number is sufficiently large so that you can be turbulent. Now, if one is honest, this is challenging to simulate computationally. But it is appealing that it's out there, and it's already in textbooks. This idea that you have these pancake eddies with strong stratification up to this Osmodov scale, then you have 3D Kolmogorov-like turbulence, and you still have k to the minus 5/3 in your horizontal spectrum, even above the Osmodov scale when you're definitely anisotropic. So, it seems appealing, but do we get it? Now, there's kind of this picture of layering in this very influential paper of Geert Brettauer, and other people have simulated it. And I particularly point you towards the Bartello and Tobias paper, because that's beautiful in explaining just how challenging this is to compute. And we did some seismic oceanography and claimed it hasn't, I've scaled it too little, and claimed that we do actually see, by looking at the distribution of density isosurfaces associated with seismic measurements that were originally looking for oil, that you do see a horizontal spectrum like k to the minus 5/3. This is k squared by the energy spectrum. This is k to the minus 1, so it's k to the minus 3, so it's the wave field, and then we see a k to the plus third for k squared by the energy spectrum. So that is indicative of this k to the minus 5/3 scaling in the horizontal spectrum. But it's just, how do you get such a flow? How can you have such a flow that is wildly strongly stratified and yet high Reynolds number? Now, there are the plots that are put down that say, well, the ocean is in this regime, but these are average values of the Richardson number and so on. And if you are in a situation, how would you get a turbulent flow that is very, very strongly stratified? The numerics is always got a body force in it. So you're artificially forcing the flow to inject energy. You're able to kick it as hard as you like, but you must remember, these people, including me, are not solving the Navier-Stokes equations. They're putting in an extra term to keep the thing alive. So how are you going to force it? Shear instability, you say. But by definition, shear instabilities have to have the Richardson number less than a quarter somewhere. So how are you going to do that? Because the Kelvin-Helmholtz simulations that Ali Mashiach has done and I've been involved in, well, I've asked him to give me a plot, you see these rolls and you see this turbulence, but they've started off at low Richardson number. So how have you managed to get this? So if you then look at how gamma varies with buoyancy Reynolds number, it goes up and goes down, and it seems to be consistent with like Damien's lake data and ocean measurements by Bill Smythe, that these quantities go up and go down and can go to very large values, which once again resonates with what Greg was talking about. You can have very large values of gamma associated with such things, but they're overturning, they're very efficient at very high buoyancy Reynolds numbers, but they are not at strongly stratified. They have to be in weakly stratified environments. And so it's not at all clear how you could get such a flow. It's not consistent with this picture. Now we see when we do these Kelvin-Helmholtz overturnings that we can say that we are able to evaluate a buoyancy Reynolds number at every instant during the evolution because, of course, the simulations, the dissipation rate shoots up, the stratification changes. You can see that they're under-resolved, and you get these very high values of buoyancy Reynolds number, so you can then say, okay, well, I can treat the flow at any particular instant as if it's sampling a particular buoyancy Reynolds number and see if that is a useful parameterization. Now, is that useful? Well, of course, there is this effort to turn the quantity we want, this dissipation, this eddy diffusivity for heat. We don't know gamma, and we can, as Greg said, we can express it in terms of the Osmodov scale, which itself, involves the dissipation rate and the buoyancy frequency. Dissipation rate's hard to measure, but the Thorpe scale is easy to measure. So if we can understand how the ratio of the Osmodov scale and the Thorpe scale varies, we then have got a mechanism to estimate this. And Karen and other people have been involved in saying, careful with that. But there's certainly an issue for the Kelvin-Helmholtz billow, because the Kelvin-Helmholtz billow, when it overturns, it has an enormous value of its Thorpe scale, and it has a small amount of turbulence, because the turbulence only switches on at sort of later stages here, when the overturn has really started to collapse. So you see this picture that the length scale, the Thorpe scale, and the Osmodov scale are evolving in completely different ways. The Thorpe scale flares up and then drops down, and the Osmodov scale comes up to some value and then decays slowly. And so this is another one of those plots. These are our numerical simulations. This is the Dillon argument that the ratio is this value, and it's the same value like a stopped clock, right? It's just never the same. And also the picture is completely incorrect, because both in such a large overturning, the overturning, they are always decaying. So if I am saying I measure the properties at this instant, what matters are the properties at this instant, or in this instance in the flow. This isn't turbulence as you might know it, because it knows that it has already come from such a large overturning. And so you could say, even if you do say, I'll look at it at this instant and work out its value of gamma, and I'll look at it at another instance and work out its value of gamma, you'll find that you have enormous values that vary with time, because I'm going in this direction in time as it slows down. And it's not really reasonable to suppose that these scalings have anything reasonable to say about a parameterization. The mixing associated with the Kelvin-Helmholtz billow is the mixing associated with the Kelvin-Helmholtz billow, and is sui generis. It is of itself. It's only like that because it's after mixing with the Kelvin-Helmholtz billow. The subsequent turbulence has always remembered it had this big injection of an overturning, which I like to say has this sort of idea of a Goldilocks mixing. The mixing is most efficient at the instant precisely when the Thorpe scale, the length scale of the overturning, precisely matches the Osmodov scale. Because that means, for your turbulence theory, the thing you want to have the most efficient mixing is the largest possible inertial range to do that cascade. That seems to be the most efficient. We don't know why, but that seems to be the case. So if your overturning scale is much bigger than that, you're wasting overturning. You're wasting energy to have an overturning scale bigger than that Osmodov scale. You want to be injecting your energy through overturning, through the turbulence, at the largest possible scale. And that appears to be characteristic of Kelvin-Helmholtz billows, which is why their gammas are enormously big compared to 0.2. But that doesn't mean that matters, because because you face the fundamental question: how in the ocean have you managed to get a flow that is perfectly well behaved until its Richardson number goes to 0.05 and then it goes off? How could it do that? Or 0.15? Why would it do that? Surely as soon as it becomes unstable, it will go unstable. Who knows? Okay, but even then that's not the end of our problems, because that is all based on this idea that you have overturning. And at least overturning is something that you have this big overturning, you'll have a sharp gradient that you smooth out. It will behave like this picture you have of a diffusive type mixing process that can be modeled by kappa T. But in a paper with Andy, with ideas dating back to Cato and Phillips, that doesn't have to be it. There's another kind of mixing that can take place, this sort of scouring. You can have very sharp density interfaces, and those sharp density, the turbulence is not able to overturn them, but it's still able to scrape a little bit of fluid up, and you can still have mixing in such scouring dynamics. And so you can indeed have that very sort of thing. And there's another instability, of course, the Holmboe instability. So you have these big overturnings, the Kelvin-Helmholtz billows. They flare up, they rapidly mix, and then they die away, but they are doing this large overturning. But Holmboe instability, these sort of propagating waves associated with vortices above the interface and below the interface, those guys can last for a long time, and they don't break the overturning at all. And Hessam Saliapur had this really good, where good is synonymous with crazy, idea to think, okay, let's look during this evolution at the properties of the flow horizontally averaged. It's turbulent as all get out, but look at the properties of the flow, just horizontally average the flow, and look at the values of the gradient Richardson number defined for the horizontally averaged turbulent flow, and plot the PDF of flows susceptible to Holmboe instabilities for a wide range of different stratifications, a factor of 4 in the value of the bulk Richardson number, a factor of 5 in how sharp the interface was to start with, always at high Reynolds number. And plot the PDF of the point-wise estimates of the gradient Richardson number. And the dashed line is 0.25. How can this be? This flow adjusts itself to being a very long-lived turbulent flow with a PDF of its point-wise gradient Richardson number, a quarter. We've all heard about a quarter because that's Miles Howard, but how can this be stable? Because it's turbulent. But it seems to be, and Hessam's keen on this idea of the self-organized criticality. And the really interesting point, for me at least in this conversation, is if you look at what gamma is for Holmboe instabilities with a whole range of different values. Remember I said the Kelvin-Helmholtz goes to very large values of gamma, and that's 0.2 for the Holmboe waves. They're long-lived, they're shear-driven, and they have Richardson number tending to about a quarter, and gamma tending to about 0.2. Now remember saying the Richardson number, remember the definition of the turbulent Prandtl number, that's also kind of saying that the turbulent Prandtl number is of order 1. But it's not saying it's strongly stratified. It's saying it's tuning to this relatively weakly stratified case where you have order what, where you have Richardson number about a quarter, flux Richardson number about a quarter, and it's just tuning itself to that. And Bill Smythe has observations in the equatorial undercurrent, this Richardson number around a quarter. And so there's issues, of course, with whether you can have instability in a turbulent flow, though Alexis Kaminsky's done a very nice paper with Bill Smythe about this, about looking at linear instabilities in flows with turbulence. But the kind of hypothesis is gamma being about 0.2 just a property of quasi-steady high Reynolds number turbulence with turbulent Prandtl number about 1. So we've also, in the MUST project, we've been looking at wall-forced flows, the plane Couette flow problem, which is very, very nice. You fix the density at two walls and you just move them past each other. And that's very nice because you guaranteed you have a constant flux. The constant flux is emergent, but it is a constant flux across the system. And we found, or Chi Zhu found, that as you vary your overall Reynolds number, that you can have turbulence up to about Richardson number of 0.2, at which stage the flow goes intermittent. And if you plot this gradient Richardson number that appears because you tune towards a Mononomikov similarity type solution, and you have a linear gradient through the interior of both velocity and density. So you have a unique definition of your Richardson number, except in the boundary layers. The flux Richardson number and the Richardson number, for a range of Prandtl numbers and overall stratifications and Reynolds numbers, sits on the 1,1 line until about 0.1617, and then it can't be turbulent anymore. Boom, it switches off. You never access the right flank. You just go up this flank, and then you can't be turbulent anymore. But that, you know, you could say that you measure a high Richardson number, but this is a beautifully tuned problem, but it's a wall force problem, which is just different from a freely evolving problem, because it goes intermittent, because as Kat already said, you have this locking between your velocity and your density in the interior, but you always have viscous boundary layers. And as you increase the density jump, now you make the Reynolds number bigger, inevitably down in the viscous boundary layer you'll have a low Reynolds number with a high local Richardson number. It won't be able to get momentum out from the walls, and so it switches itself off. And that's a fundamentally different dynamic because it's boundary forced. Fundamentally different dynamic, but the boundaries matter, as Matthew said. So we have to understand boundary force problems. So what happens if you force it from sidewalls? And so there's this thing we've been doing, we don't really understand it fully, of looking at Taylor-Couette problem, rotating in a cylinder, stationary outer cylinder, and vertical stratification. You do PIV, you get very, very close to constant angular momentum, except for boundary layers, which means you have a 1/r velocity profile. You start off with a linear stratification, and layers spontaneously form. You can't maintain a linear stratification, you get a spontaneous forming of layers. Now, such things are prone to stratorotational instability, but the layer dynamic is highly turbulent. So if you look at an individual interface, this is a shadow graph of an individual interface, and you see that you have this sharp interface, and then you have a quasi-periodic signal that appears, that mixes the interface up, but then the interface reposes. And if we start off with a multiple, with a linearly stratified flow, it spontaneously forms layers, which has this on-off switching mechanism of there's an interface, then it's turbulent, then there's an interface, then there's a turbulent. You do a pixel line here, and you match it up like the Bayeux tapestry, and you see, as you scroll by, you see an interface, turbulent process, interface, turbulent process, interface, turbulent process. So you can have interface layer dynamics, which has intermittent spatiotemporal mixing processes that rebuild the interfaces. These layers are extremely well long-lived. The mixing appears to be the independent of the structure, and you have this spatiotemporal intermittency is inevitable in your particular flow. Okay, so which Richardson number do I use? Do I use a Richardson number associated with when it's a sharp with the mix layer, or with the interface, or not? Who knows? So, Kelvin-Helmholtz instability, it knows about its big overturning. The Holmboe instability, it lasts longer, and it seems to be kind of quasi-steady. If I force at the walls, it's always weakly stratified. It has this Prandtl number, order 1 situation, and then it can't go turbulent anymore. So then, let's go over to the side of forcing a flow. Let's say we force the flow, and we force the flow so it has to be statistically steady with a constant shear and a constant buoyancy frequency. But I allow the choice of the buoyancy frequency to vary, just to see if we can isolate all the other effects and only have the intensity of the turbulence. So these are quite heroic simulations being done by Gavin Portwood, one of Steve de Proincot's students, with up to, whatever that is, 100 billion grid points. I'm glad I'm not analyzing them. And the way he does the calculation is you choose the how much turbulent kinetic energy you want. You then choose the viscosity. Now, ultimately, that will then determine what your buoyancy Reynolds number is, but it's emergent. You don't know what it is. You then require the flow to be steady, and you imagine you're in a spaceship where you can change gravity. And you oscillate, you have a constant shear and a constant density gradient, but you change gravity until the flow evolves to a statistically steady state. And so the particular value of n squared emerges, the particular value of the dissipation rate emerges, and the particular amount of the partitioning between kinetic energy dissipation and stratified mixing is also emergent. We don't fix it. It's amazing. Across a range, Steve de Bruyne-Cox likes calling the buoyancy Reynolds number the Gibson number, for reasons that I'll explain to you over an apero time. But over varying between 36 and 900, big ass number, we always get this flow self-adjusts. So the Richardson number is 0.16. It self-adjusts, so the turbulent Froude number is 0.4. It self-adjusts, so the turbulent Prandtl number is 1, which then means for Greg's D is 1 over gamma, and his density scale for this problem adjusts to the Caulfield scale, because turbulent Prandtl number means that the density scale is going to match to the shear scale, but that's unique to this particular problem. And if you filter everything out, and so therefore this is definitely a steady turbulent flow at a finite Richardson number, gamma's 0.2. For buoyancy Reynolds number up to 900. Bloody amazing. And it contradicts many papers by Caulfield and co-workers. But it seems that this parameterization is characteristic of steady, shear-forced, weakly stratified, and it's critical is this weakly stratified, so it's on the left flank. And in such a dynamic, the turbulent Prandtl number is very close to 1, and so therefore the Osborn parameterization in that case is equivalent to the Osborn-Cox parameterization. And but the thing is, the Richardson number's about a quarter. But I don't know whether there is any meaning to the Miles-Howard situation, or whether this is just an adjustment that is natural for such turbulence. Okay, so that's what I wanted to talk about. So I'll come back to the open questions. I got that book for Christmas, and I think it's highly appropriate to this particular problem. So the open questions are: what does a Richardson number actually mean in turbulent or spatio-temporally varying flows? If it varies in space and time, how can we use it as a parameter? But we want to use it as a parameter because it means something physically to our intuition. And then also, does stability theory have any relevance at all? I mean, the picture that Matthew showed of Craig Winter's simulation, I agree completely with his interpretation that those are shear instabilities. But the mathematician in me says, but it's time evolving, it's turbulent, how can it be unstable? There's a certain time scale of which the instability grows, yada, 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 yada. But it still happens. Do force flows have any connection with freely evolving flows? I don't know. It doesn't seem that case because the particularity of the forcing seems to be so much understood by the flow. How can the history or the memory, and indeed I haven't even talked about stuff about advection coming in and out of my domain, which is an order 1 thing that Matthew was saying. We seem to get layered states, which links back to the fact that Richardson number inherently can be spatio-temporally variable. But are they generic, or can you even get them? And in particular, can you have non-monotonic flux laws? Can you actually have a region where there is a high Richardson number? Or is the high Richardson number always looping back to be the same as the low buoyancy Reynolds number? And so, and that is, you are not going onto the right flank of the Richardson number, but you're looping back to being on the left flank of the buoyancy Reynolds number, and vice versa. When you're at high buoyancy Reynolds number, are you inevitably at low Richardson number, so your mixing is less efficient? It's not, we don't know. I don't think we have a clear answer, but we don't really know. All my papers ignore the effects of boundaries, but they're order 1 important for the real problem. And so then that is the real challenge. Is there any hope to use such deterministic physics-based methods to describe stratified mixing? Is the future just data-driven? Because do we need to consider all possible processes, or indeed try and learn, which is something, again, that Hessam is suggesting, and in my role as JFM, it seems every second paper is deep learning convolutions of something. So is that the future? So that's the end of my talks. Of course, I put the slides together. Here's the cast of 20 involved, an army of wonderful PhD students. The blue ones who've graduated, the black ones are still going on. Similarly, the postdocs who are involved in this from the MUST project, the blue ones have gone on to CNRS positions and honorar positions and faculty positions and machine learning startups. And then, of course, I'm very fortunate to work with senior collaborators. The ones in blue are the other co-Is on the MUST project, who I've been very privileged to work on. And, of course, Paul Linden and Dick Peltier have had the order zero influence on my thinking on this particular problem. So they're the sort of, in purple, the emperors of this particular problem. So if you'd like to see the longer version of this, of course we're going to be doing it in the summer in Woods Hole. But thank you very much for your attention.
Thank you so much, Colm, for a wonderful talk, and a lot of time and thought in there. And
While you were skiing.
I certainly approve the grand challenge. Let's take billions counts. Challenge. So we've certainly got a bit of time if there's any questions for Colm. And we'll use the microphone because we're recording these.
Thank you for a lovely presentation, and I will say, especially for the Celtic animation, that your kindred spirits from Southern Europe definitely appreciate. So I have a question that's personally biased, and it goes to the existence of the last regime, right?
Yeah.
And this is a question that I think I've asked with Jim Riley, Steve DeBrunkhoffs, and Jeff Spedding. The wake problem is a decaying problem that is somewhat more realistic as a process, physical process, but still idealized, where we're seeing evidence, at least in a numerical simulation context, right? Like a implicit large eddy simulation where a very big part of the spectrum is captured, down about 20 Kolmogorov scales, that you enter gradually into this regime where your vertical Fru number is 1, your horizontal Fru number is much smaller than 1. There's some uncertainty in the dissipation rate, and we're going to figure this out. I do think you get a high enough Gibson number, activity parameter, buoyancy Reynolds number, whatever you want to call it. So the question that we've been asking is, why does the last community, or I don't know what the people that look at these box turbulence problems, even though the wake motivated a lot of these questions to connect with Lilly's theories and whatnot, why is the wake problem very overlooked in some cases? I mean, I don't know if that's the right word, right? But I think this is evidence that this is happening in something a little more realistic.
No, I think that's my guess is somewhat connected to this kind of thing about the Rorschach test, right? So there was the argument was presented that the wake is in a situation where its buoyancy Reynolds number decays. You of course know the argument, right? You know what? It's decaying out, and the original beautiful experiments by Jeff and from 25 years ago was then it would say, okay, those pancakes are in the sort of Lilly viscously affected regime.
Viscous doom was Jeff.
We've kind of, and I think the issue is that the community, the particular community interested in this strongly stratified thing, have then turned away and thought that that's the answer. But of course, you and Chi in particular have got to much, much bigger simulations, and so then you could be possibly in this regime. And so that's an example. Such large wakes for a certain period of time may be in this regime. And the question is just how important such large wakes are for the ocean mixing problem as opposed to other problems.
Yeah, other problems. There we go.
We are being recorded.
That totally covers me. Thank you.
Great talk, Colm, as expected, so thank you. Maybe we can just pick up on one little point, in fact your last point, which is really interesting. Is the future data-driven?
Yeah.
So I guess the question really is, if you're actually making measurements in the ocean, what is the data? The reality is, to infer any of these quantities, you actually have to use finite length time series or finite records in scales in the vertical from probes, say, that Matthew was talking about.
Yeah.
So those data then is used in spectral theories to obtain estimates. So we're getting bulk averages. So what do we really mean by is the future data driven? It's not instantaneous point measurements, because we'll never be able to get ensemble averages of any significant thing. We can only use these statistical methods which restrict us in what's the advice? You know, what are we looking for in terms of time and space measurements to make that can actually contribute? What data are we talking about in the future?
Well, I think obviously I'm thirsty. I think that the point I was trying to make was actually related to something you were saying in your talk, and other things I've talked to Matthew about, and also John Taylor. We've been talking about this. What I mean by data driven is, if we continue to see this explosion in computational power, is to simulate a class of flows and then synthetically sample them in the way that you can synthetically sample them in the ocean. And so from that synthetic sampling of the data that you know everything about, the numerical data that you know everything about, you can then get better inferences of what the real measurements are telling you about the larger flow. And that's what I mean about data driven. I think the answer is going to be, we'll just do these big suites of simulations, and then we will sample them like the cleverest people who are making the machines to sample, compare the data that comes from the numerical simulation. If it looks like A, which is measured by the oceanographer, that implies B for the quantity we're interested in, because we know everything from the numerics, but we can't possibly know everything from the ocean. And I think you're right where that problem is, but I think the bottleneck is, does doing physics rather than statistics help us on analyzing the increasingly bigger and bigger and bigger simulations we're able to do? And I'm 50 and I've got, midlife crisis about it. I don't know if that's the answer, right? I'm unsure about whether these physical-based models are actually misleading or not, because they come with these views of that there are things that are sort of thought to be self-evident that then are maybe not self-evident.
Okay. So thank you very much. Very exciting. I have understood 10% maybe, but
it's about 5% more than I do.
Okay. So I see here missing a lot of the discussions that in physical oceanographers, numerical modelers do about sub-mesoscales.
Yeah.
And, mesoscale, large scale, mesoscale, sub-mesoscale, near inertial waves. So is that what you mean by saying that we need to look at, yes, for exactly this one?
So,
okay, so give me some input, please.
I put a hierarchy of 4 scales here, and there should be a 5th, which I was humming and hawing about, like an LR, a Rossby scale.
Yeah.
So this is all about, this is enormous, but is tiny compared to rotation. Yeah. And that is another issue about this, because, this has to be very, very big, but still small compared to, let's say, a 10-kilometer scale. And so it's got an interesting window of opportunity. And I think he met, we all play this game. We all play this game about trying to guess who referees are. And when I've written about this, people say, well, yes, but this is clearly, you're all looking at a regime which is completely not affected by rotation, and rotation is critically important. And we've started to understand the sub-mesoscale, smaller and smaller scales have a non-trivial effect of rotation. And I've always been ignoring that, and that's another problem along the other side.
But rotation is in your history.
Yes.
If it is true that you first have the larger scale and that there is no doubt rotation.
Yes.
Mesoscale, no doubt rotation.
Yeah.
Sub-mesoscale, also rotation. So then from the sub-mesoscale on. And actually, to me, that two opposite currents there is like your Couette flow.
Yeah, yeah. No doubt. I don't disagree. Yeah, because then again, that there is like our data, the seismic oceanography, it's entirely possible that these patches are actually sub-mesoscale eddy, and the major component is not this velocity, but is actually a spinning round out of the. They're largely got vertical vorticity. Absolutely, and that's another can of worms.
Thanks again also, Colm, for the talk. It was great. For the parameters estimation, you discussed a lot about the dynamics, and you said there's really a need to understand what we estimate or how we measure it. Yeah. What about N? Like, it's everywhere in all the definition we use.
And even that is an that's a very interesting point. So, from my education, I always thought of the N as an outer scale. As in, that came in from the background, and the turbulence is small compared to this N. But often in these estimations, like the estimation of the Thorpe scale and so on, the N is constructed from the resorted overturning. So in a sense, it's just as local as the overturning, what the stratification is. And that is another issue. What do you actually mean by when you're talking about N? Do you have a vision that there is some outer characteristic scale that we all get from these large profiles? Or is it actually, when you look closer, is it serrated? And is it dynamically changing? And so that then leads to major issues about, this comes to, I'm not in any way, he's absolutely my intellectual hero, G.I. Taylor. The observation that, the statement that turbulence could survive at high Richardson number was really, in terms of a large bulk N, that doesn't mean a big N and a small s averaged over a large scale. You can still have turbulence inside that somewhere. But I think actually what that means is very much resonating with your question. It is somewhere in there, N is small and S is big. And then because if you have that spatial variation, then all bets are off, and you could have some vigorous patch of something going on. So it's a real challenge, therefore, to the parameterization. It resonates very much with Greg to say, we've all got excited about the Osmodov scale, but it can be very, very misleading, because what do you average the epsilon over? What do you average the N over to construct it? And, I ended up in religious debates with various postdocs about the correct way to average epsilon in a numerical simulation to give an honest measure of a buoyancy Reynolds number. Because how do you average it? And it's almost, there's an interesting question. So we did this, Gavin Portwood did this, where we have a very low Froude number simulation, which is highly intermittent. But if you conditionally sample the regions that are turbulent, the buoyancy Reynolds number in that turbulent patch is exactly the same as in the place where it is low Richardson number everywhere, high Froude number everywhere, and the turbulent patch fills the whole domain. So it's really sometimes the case where you say you have a low value of buoyancy Reynolds number. It just means you're spatiotemporally intermittent. Like turbulence is turbulence, maybe, but you have weak turbulence when you have it infrequently.
I think actually looking at time, I think it would be best to give Colm a bit of a break, and say thank you once again for all the time and effort. It was a wonderful talk, Colm. And I suggest people make their way just directly from here.